Hello, game theorists. Today we are still in Chapter 7. We're looking at mixed strategies. So in our previous episode, we looked at 3x3 games. So what we did is we found the expected payoffs. Then we took partial derivatives and set them equal to 0. Now everything worked out cleanly in our last example with rock, paper, scissors. Sometimes, however, when you go through that same procedure, some weird stuff will happen. So I'll show you some examples and also show you what to do when the weird things occur. So let's say we have this game. So we have Richard over here, and Richard can play A, B, or C. We also have Allie, who can play X, Y, or Z, and here are the payoffs. So let's say Richard plays A with probability PA, plays B with probability PB, plays C with probability 1 minus PA minus PB. Allie plays X with probability PX, Y with probability PY, Z with probability 1 minus PX minus PY. So we'll start by looking at things from Allie's perspective. I'll find Allie's expected payoff. So one possibility is that she gets 2 if AX occurs. The probability of that happening is probability Richard plays A times probability that Allie plays X. Remember, the column player's payoffs always come second, so that means Allie would be getting 2 in that case. We could also be over here, so that's if AY happens, Allie gets 0. The probability is PA times PY. So PA is the probability Richard plays A. PY is probability Allie plays Y. So PA PY is the probability of Allie getting nothing. We could also be over here, so we have 0, and the probability is PA times 1 minus PX minus PY. We've got another 0, so that could be if Richard plays B and Allie plays X. So PB, PX is the probability over here. Allie gets nothing. We could also be in the middle here. That happens if Richard plays B with probability PB and Allie plays Y, probability PY. So 0 times PB, PY. Allie gets 1 over here. The likelihood is that Richard plays B with probability PB, and Allie plays Z with probability 1 minus PX minus PY. Last row, we could be over here. Allie gets 1 in that case. The probability is that Rich has to play C with probability 1 minus PA minus PB. And then Allie has to play X with probability PX. We could be here, I gets nothing, and the probability is 1 minus PA minus PB for Richard playing C, and probably PY of Allie playing Y. And lastly, we have this over here, this last 0 from Richard playing C, probably 1 minus PA minus PB, and at the same time, Allie playing Z, that's 1 minus PX minus PY. So you can tell I rigged this example with lots of zeros, so the math works out cleanly. So that goes away, that goes away, that goes away, that goes away, and that goes away, and all that goes away. What we're left with is 2PA PX, bunch of cancellation. We still have this though, so I'll just go and expand that. Plus PB, PB times minus PX, so minus PB PX. PB times minus PY, so minus PB PY. This term does not go away, so I have a 1 times a PX, so that's PX minus PA times PX, so minus PA PX minus PB times PX, so minus PB PX, and the rest of the stuff is all zeros, so that went away. Alright, so I found Allie's expected payoff. Now I take partial derivatives. So which partial derivatives do I take? So in our game, Allie controls PX and PY. So you take one partial derivative with respect to PX, take the other one with respect to PY. Let's start with PX. So the partial derivative of this with respect to PX is 2PA. No PX's here. We treat that as if it were a constant. Derivative of constant's always 0, so that goes away. This has a PX, so that partial derivative will be minus PB. No PX's here, so that's all just constants and goes away. We do have a PX over there, so that partial derivative will be 1. Minus PA is a PX, so that partial derivative is minus PA. Minus PB times PX, that partial derivative is minus PB. So set that whole partial derivative equal to 0. So what I get, if I just combine terms here, 2PA minus PA is just 1 times a PA. Minus PB is minus 2 PB. And we still have that plus 1. Alright, so we got our first partial derivative down. Next step, take the partial derivative with respect to PY. So there are no PY's here, so that whole thing is a constant. goes away. No py's over there, so it's a constant, goes away. Still no py, so these are all zeros when you take the derivative. Okay, now I've got a py. Partial derivative of minus pb py with respect to py is minus pb. That is not a py, so it goes away. Not a py, goes away. Not a py, goes away. So that whole partial derivative is just minus pb. So that partial derivative equal to 0. So what does that give you? So minus pb equals 0. That means that pb is 0. You can then plug that in over here. What does that give you? Well, we have PA minus 2 times PB, but PB is 0, plus 1 equals 0. So that's going to mean that PA plus 1 equals 0. So 2 times 0 is 0, so that just goes away. I'll push that 1 to the other side, and I find that PA equals negative 1. So you probably found that rather troubling. That's because PA is a probability. So in our game, PA is the probability that Richard plays A. So we're saying that Richard is going to play A with probability negative 1. That's determined because probabilities can never be negative. So as I said at the beginning, sometimes when you do your math, you get something weird like that, and that can be confusing. So what's actually going on here? How on earth do I get a negative probability? You might possibly freak out, don't do that, or you might think, I must have made a mistake somewhere. This math was done by Professor Wilson, so you know there must not be any mistakes. That's impossible. So if there are no mistakes, then how did I get a negative probability? So whenever you get a negative probability, it means that there's a dominated strategy somewhere. And we should have eliminated at the beginning, but we must have overlooked that. So what strategy here was dominated? So you look at Allie's possibilities here, you notice that strategy Y looks rather disappointing. Y always gives her 0, but these other strategies, X and Z, give her positive payoffs. Sometimes, at least sometimes. You have to get 0 at those too, but at least there's a chance of getting something with X or Z. So it turns out that a mixture of X and Z dominates Y. So you play, for example, if if you played, you can verify this on your own. If you played X half the time and you play Z half the time, on average, that's better than playing Y. So mixing X and Z dominates Y. So if Y is dominated, we should have just eliminated Y from our game and worked from there. So what you gotta do is you chop out Y and you start over. So this reinforces a point that I made earlier. We had that episode on dominance by a mixed strategy. I said that's important to look for dominance because it can save you a lot of time. So here, we went through a whole bunch of math, and then we found out, oops, gotta go back and chop out Y and start over again. If we had done things properly and searched for dominant strategies first, we could have saved ourselves that whole nonsense. So I knew it was going to happen, but I wanted to work through it anyways so that if you somehow stumbled into this kind of situation, now you know what to do. So you handle these games same way we did earlier. Find expected payoffs, take partial derivatives, set them equal to 0. If all your probabilities work out nicely like they did in rock, paper, scissors, then you're done. If you get something negative, then look for dominated strategies. Ideally, of course, you should look for dominated strategies at the outset, but if you didn't, this is how you would find that you had overlooked them. So that's one example of some weirdness that can happen in games with mixed strategies. Be sure to tune in for our next episode and learn about some other possible weirdness and how to deal with it.